Okay, let us proceed now for the isothermal process. Okay, for the isothermal process is an internally reversible constant temperature process of a working substance. Okay. Under the pressure volume diagram or PV plane, pressure volume, as the pressure decreases, the volume increases. As the pressure decreases, the volume increases. As the pressure increases, the volume decreases, vice versa. Inversely proportional. As the pressure increases, the volume decreases. But as the pressure decreases, the volume increases. This one is your V1. This one is your V2. This one is your P1. And this one is your P2. Pressure, volume is constant. 1 to 2. For the TS plane, temperature, entropy. Even the pressure, the entropy increases, the temperature remain constant. Okay. 1 to 2. Okay, relationship for letter A. Relationship between the pressure and volume. We have P1 is equal to P2 V2. Letter B. For the non-flow work, we have integral of P dV with the limits from 1 to 2. That is equal to P1 V1 is equal to P1 V1 ln. P1 V1 ln V2 over V1. But your P1 V1 is the same as P2 V2. Therefore, that is also equal to P2 V2 ln V2 over V1. From this one, your V2 over V1 is equal to P1 over P2. Therefore, this one is equal to P1 V1 ln P1 over P2, which is also equal to P2 V2 ln P1 over P2. But your P1 V1 from the ideal gas law, we have PV is equal to MRT. Therefore, P1 V1 is equal to MRT1 ln P1 ln P1 over P2 equal to MRT1 MRT2 ln P1 over P2. Or this one is MRT1 ln V2 over V1 or MRT2 ln V2 over V1. Okay, for delta U, change in internal energy, that is equal to 0. While letter D, for the heat, the same formula as your non-flow work. Okay. And then for letter E, delta H, which is the change in enthalpy, is also equal to 0. And then for the change in entropy, delta S is equal to heat over the temperature, or that is also equal to MR ln P1 over P2. P1 over P2, P1 over P2 is V2 over V1. Therefore, this one is equal to MR ln V2 over V1. Okay, for the steady flow isothermal, your steady flow work is equal to heat, which is the same as the non-flow work. And for negative integral of V dP with the limits from 1 to 2, that is equal to steady flow work plus change in kinetic energy. But if the change in kinetic energy is equal to 0, therefore negative integral of V dP with the limits from 1 to 2 is equal to steady flow work, which is also equal to heat, which is also equal to the non-flow work. Okay, example, the temperature of an ideal gas remains constant while the absolute pressure changes from 103.5 kilopascal to 750 kilopascal. Letter A, if the initial volume is 75 liters, what is the final volume? Letter B, for 180 grams of the gas, determine the change of density expressed as a percentage of the initial density. Okay, now for the system. Okay, ideal given state 1 process state 2. Okay, P1 is equal to 103.5 kilopascal. V1 75 liters. Tapos mass is equal to 180 grams. Convert into kilograms. 180 grams times 1 kilogram is equal to 1,000 grams. Okay, therefore, this one is 0.18 kilograms. Kilogram constant. Process isothermal state 2 P2 is 750 kilopascal. Diagram. Diagram. Under the PV plane. Okay. From 1 to 2. Why 1 to 2? Because your P1 P1 increases, but your volume, as the pressure increases, the volume decreases. Then TS plane, temperature, entropy. TS plane. Even the entropy decreases, the temperature remain constant. For letter A, the requirement is your V2. The formula, you have P1 over P2 is equal to V2 over V1. For V2 is equal to V1 times P1 over P2. Okay, therefore, your V2 now is equal to V1 is 75 liters. 75 liters. Convert 1 cubic meter is equal to 1,000 liter times P2, P1 is 103.5, 103.5 kilopascal, P1 over P2. Correction. P1 over P2 over P2 is 750 kilopascal. 750 kilopascal. Cell V2 is equal to V2 is equal to 0.0104 cubic meter. Letter B. For letter B, the change of density. Letter B. For one, determine the change of density. And therefore, change of density expressed as a percentage of the initial density is change in density over rho 1 is equal to rho 2 minus change in density is equal to rho 2 minus rho 1 over rho 1. Okay, from the formula, P is equal to rho R T, we have rho 1 is equal to P1 over RT. Since temperature is constant, your T1 is the same as T2. T1 is the same as T2. Okay, therefore we have, for constant R and T, we can say that your rho 2 minus rho 1 is equal to 1 over RT times rho 2 minus rho 1. Okay, then substitute, change in rho over rho 1 is equal to 1 over RT times rho 2 minus rho 1 over rho 1 is equal to P1 over RT. But 1 over RT P2 minus P1. Correction with this one. This one is P2 minus P1. Wait, okay, since your rho 2 minus rho 1 is equal to P1 over RT minus P2 over RT, okay, therefore, common factor is 1 over RT. 1 over RT times quantity P1 minus P2. This one is P1 minus this one is O2 P1. O2 since rho 2, therefore P2 over RT minus rho 1, P1 over RT. Okay, therefore, that is P2 minus P1. And therefore, this one is P instead of rho. And therefore, this one is P2 minus P1. P1. Okay, therefore, this one is P2 minus P1. Okay, therefore, we have cancel RT, therefore we have P2 minus P1 over P1, which is equal to P2 is 750 kilopascal. 750 minus P1 is 103.5. 103.5 kilopascal over P1. P1 is 103.5 kilopascal. Cancel the unit. Okay, therefore, times 100, your change in P equal to, okay, therefore, this one is 6.25 times 100%. Okay. Therefore, the change in density per rho 1 is equal to 625%.